So next speaker is Xiaolong Wang from CMU. His advisor is Abhinav Gupta, and he previously worked at FAIR with Kai-Ming and Ross. His work is well known for learning visual representations. Today he's going to discuss adversarial learning in detection and action.
Thank you for the introduction. So I'm Xiaolong. Today I'm going to talk about adversarial learning for object detections in computer visions, as well as taking actions in robots. So from previous tutorials, you have already know how to generate beautiful images with GANs. So in this tutorial, I will be talking about how to use this adversarial learning to perform different tasks, not just image generations. So the key idea here is to find the adversary task for your target tasks. So in that case, you can improve your target tasks by fighting against these adversary tasks, like these two kids fighting against each other. So what does it mean in computer vision? For example, in object detections, if you want to recognize this bird, one adversary task would be actually adding occlusions. So you can basically train a language to generate a mask to occlude the bird's head and the bird's leg. And this will make the recognition hard, and your detector will need to conquer these difficulties proposed by the adversarial networks. And from that, your detector will become robust to occlusions. And the other adversarial task for object detections will be basically deformations. So you can train a network to rotate or perform deformations on these images to make the detection hard. And in the scenarios of robotics, for example, in grasping, so if we want to have a stable grasping, one of the adversarial for stable grasping is actually shaking. So if your grasping is stable enough, the object should not fall down. So this is actually an example of unstable grasping. And the other example is SNATCHING. So if your graph is really stable enough, you can train another policy which is performing the SNATCHING from the other hand. And this hand is trying to steal the objects from the grasping. And if your grasping is stable enough, the other hand should not be able to steal it. But in this case, because the grasping is not so stable, so the other hand is successfully snatching the objects to the other side. So this is basically the ideas. We can define different adversary tasks for our target tasks. So in the first part of this tutorial, I will first like to introduce our work in adversarial object detections. So before showing you how we actually do the detections, I want to show you some failure attempts when we're starting on these projects. So we starting on these projects learning to generate beautiful images. And at that time, we can generate reasonably good. Now it's not so good compared to current GAN papers on these scenes. And then we run the detectors in these generated images. And we can find that you can actually find a lot of objects with the detectors in these images. So that we think maybe generating these images can be an extra training data to train the object detectors. So is that really the case? So we're following this idea. We try to generate images with DC GAN in COCO. So because it's not a conditional GAN, and it's not even conditional to the class. So what we can do at that time with DC GAN is pretty random images when you train in the whole COCO data set unsupervisedly. So we say, maybe this is not good enough. We can just take it as a negative examples, augmenting the negative data in training the detectors. And the good news is, it doesn't hurt the detector. And the bad news is, it doesn't help as well. So why is that? Because this kind of images actually does not exist in the testing data. So even the detector is be able to conquer, to recognize this is false, this is not real, it doesn't really help detections. And in the other way we try is using actually conditional GAN. So given a small resolution images, we try to use GAN, for example, learning to do super resolutions. And then in this way, we can add some details into these small resolution images. And saying maybe adding some details can perform some form of data augmentations. However, this does not help detection as well. Why is that? Because if you train the super resolution network on the whole COCO network, you actually cannot learn to add semantically meaningful things into images. For example, here, you can see the face. The SR GAN has not added any ears or eyes or mouth on the face. So this is not useful at all. Of course, we have also tried adversarial examples, like seeing whether training detectors robust to adversarial examples can help detections. And the same reason is adversarial, you don't have the adversarial noise in the test set, so it doesn't help detections. So instead of generating images, what we propose here is we try to generate hard positive examples by modifying the positive object we have in feature space. So what we do is we can add occlusions to the objects in the feature space. And the other way is we can add deformations or rotations to the object features so that making all these adversarial tasks to challenge the detectors. First, why do we need to care so much about the positive data? So, because in object detections, in computer visions, what we usually do is we will transform the object detection task as the image classification task. So you basically crop different regions in the pictures, and then classifying this region is to a few different classes of foreground classes or a background class. But the problem is there's large number of background classes. It's overly outnumbered compared to the foreground classes. So it would be really nice if we can generate more and more foreground classes. So what we do here, the first strategy is to adding occlusions in the foreground objects in feature space. So what we do here, for example, for this bike, in the feature space, where in spatial is 6x6 dimension and cross-channel numbers, and we can basically use the adversarial network to generate a mask. And in this mask, the darker the region is the more high probability that you will try to drop out the features in that locations. For example, here, our adversarial network suggests us to drop out the wheels of the bicycle to make the recognition much harder. And here are more examples. The adversarial network learn to drop out the faces of the human to make the detection hard, and also the faces of horse and other parts of the birds. So, so before showing you how do we train this adversarial dropout network, I would first like to introduce a little bit the standard pipeline of the object detector, state-of-art object detector, fast RCN. So what you do is you input an image into a convolutional network, you extract the features for the whole image, and then you crop the features according to the proposal bounding box. And then these crop out features are resized to channel cross 6x6. 6x6 is in spatial dimensions. And these features is the object features you want to focus on. And you use these features to perform classifications or bounding box regression for detections. So this is the standard pipeline. So what we do here is we're adding something in the middle. We basically add this adversarial spatial dropout network. So these features, extracted features, is forwarded to a small network, and this network will generate a mask. And this mask is telling you in which place in the spatial locations to drop out the features to make the features hard to recognize by the following classifiers. And following are our training methods. So we will try to train the fast RCN without the adversarial networks. So in this way, the high-level features will get a sense about how the objects should look like. And then we fix this fast RCN, and we plug in this adversarial dropout networks, and we initialize this adversarial dropout network in a relatively brute force way. What we do is we were trying to perform sliding windows on the crop objects. What does it mean? For example, for the car in the For in the card in the right bottom, we perform a sliding window saying this small box is the place we want to drop out the features. And we slide this small box, and for every dropout and every different strategy of dropout, we generate a new features. And these features are forwarded to the classifiers. And then you basically select the classifiers, the dropout policy that give you the highest loss. For example, here, we find that we drop out the wheels of the cars will give you the highest detection loss. And then we will say, this is a good mask for us to challenge this detector. We basically use this mask as the ground truth to train the adversarial dropout networks. So next time, when you forward to the same card to the detector and adversarial network, you will note where to drop out will give you a very challenging features for the detector to recognize. And in the first stage, we're basically training all the things joined together. So we no longer use sliding window to select the mask. We are actually using the mask generated by the adversarial networks. So it is a two-stage alternative training. So you can optimize the fast RCN by the dropout mask, by using the dropout mask and apply it on the features and modify the features and do classifications. So the detector should learn to handle all kinds of different weird kinds of dropouts. And then you also select the best dropout policies which give you the detector the high loss to optimize the adversarial network. So in more detail, the way we do it is, for example, if we have this card, the man on the motorcycle, and we can generate this kind of mask. And we then perform sampling on this mask. So these masks, the darker regions represents the higher probabilities to drop out the spatial locations. And you can basically perform different types of sampling on this mask to generate this 0-1 mask. Black represents drop out all the channels in the spatial location, and white represents maintaining the same. And you forwarded the modified features to the classifiers. And then you can select the one which gives you the highest loss, basically. And this mask is then selected as the ground truth to training the adversarial dropout networks. And we use basically, it's like a segmentation task, but this mask is automatically generated by the policies. And we use a binary cross-entropy loss to optimize the adversarial dropout network. So here are basically more examples of the dropout masks generated by our adversarial networks. So the network can figure out where to drop out the objects to make it hard to recognize for detectors. For example, it learns to draw out the wheels, and a lot of times it draws out the faces of humans and the heads of the animals, and sometimes the bottom of the plane. Besides using this smart way of dropout, another way to do adversarial training is actually performing deformations. And in our case, it's actually rotations. So here, we propose another small network called adversarial spatial transformer network. So remember, the spatial transformer network is originally proposed to align features of the objects to make object recognition much easier. However, in this way, in this talk, we are going to do it in the opposite way. We want to use this spatial transformer network to actually make recognition harder. So in this way, the detector should still recognize the object, even the object is transformed. The feature is transformed. But a simple way to transform the object features to be hard will be rotate the objects upside down. So in this case, we are actually adding more constraints to the rotations. For example, we only allow rotations to within around 10 degrees. And then we actually divide all the channels into different parts. And different parts of different channels should actually have different kinds of rotations. So in this way, it will not be all the channels rotate to the same angles. It's just making the challenge much harder. So here is basically one illustration So actually rotating the features does not really corresponding to rotating the images in this way. It is just examples of illustrations. So these two small legwork can actually be trained together. So given the features, object features, you first forward it to adversarial dropout legworks to perform some dropout, and then you can, these features can further be transformed by our adversarial transformer legwork. And these two legworks are only used in adversarial training during training time. And during testing time, we basically remove all these adversarial legworks and test as the simple, easy, fast ASEAN. So we have done our experiments in the Pascal VLC dataset. So at that time, we are still starting with LXLeg and VGG16. For these legworks, we can basically find both strategy give you around 1% improvement, and together it's around 2% improvement. So you will wonder whether this strategy would work on the much deeper legwork. So later, we actually experiment on ResLeg 101 for detections, and we can see that even for such a large legwork, we can still have a reasonable improvement around 2%. And here is basically some ablations. So random dropouts actually doesn't give you much improvement, around 0.3%. And if you use a fixed adversarial dropout legwork, the fixed adversarial dropout legwork basically means finishing the second stage of training, only using the sliding window strategy to train the dropout legwork. And it's not updating during the joint learning, so you cannot get feedback from the detectors. So in this way, it is slightly better than random dropout. However, if we train all the legworks joined together end to end, we can have much better improvement. And similarly, in the case of spatial transformer legwork, we also have similar improvements. So the code is online, and we are welcome you to use it. And we later have also tried our experiment on the much larger data set, a COCO object detection data set. So in this large data set, we can still find reasonable improvement. In AP50, we have around 3% improvement. And then in the average AP, we have around 1.5% improvement with VGG16 network. So following, I'm going to show you some examples about the adversarial detection results. So it's be able to find some occluded objects. So for example, here it finds the humans out and the chairs in the behind. And the other cases, the baseline didn't find the dogs on the left, and our legwork can find the occlusion objects. Interestingly, the occlusion objects is actually labeled as cow. So it's actually a little bit overgeneralized. And we also have some more examples about overgeneralizations. So, sometimes the leg will recognize this man as the bird, and this dog as a sheep, and on the bottom left is the boat, basically. So far I have introduced designing this all adversarial strategy for object detections. But this framework is so general that we can actually apply on many different tasks. For example, a lot of tasks we can perform on is actually the adversarial grasping in robotics. So in the beginning, I want to show you that there are actually a lot of advances in the self-supervised grasping. So for those who don't know, so self-supervised grasping is basically there's a tons of objects in the table, and you just use your robot randomly grasp the objects. And if you can grasp up objects, it is a success. If you don't, it is a failure. The success and failure basically becomes your supervisions to train successful grasping policies. But actually, even you keep training, like Google, you have so many robots keep grasping day and night. It is still not enough. Why is that? So in these following cases, these two cases are all actually the same successful grasping for the robot. However, on the right, it's actually not a stable grasping because you are trying to grasping in the end of the handle of the gun. So this grasping strategy is not stable. The goal here is we want to make the grasping more stable. Before showing you what the robot will do, I would first like to show you what the children will do. So in this video, this baby is grasping a toy, and this grasping seems to be very stable because she's trying to doing all these manipulations and shaking and chewing these objects, and it's not falling down. And we basically want the robot to do the same thing. And in the other way to challenge the baby is actually using another baby. So in this case, this baby is trying to drink the bottle of milk. Because his grasping is not stable enough, so the other baby can actually steal the bottle from this baby, and he's not so happy. So the key idea here is still to design different adversarial agents to challenge your target agents. And then by conquering these difficulties by your adversarial agents, you have a better policy in your target agents. So one strategy is basically using shaking. So we basically can train a leopard not only grasping, but a leopard for shaking. So you keep, after you're grasping, you just shake your objects to verify whether it is a stable grasping. Here are two examples. So on the left, you can basically see it is not a stable grasping because after shaking, the object falls down. On the right, it is a relatively more stable grasping because after shaking, it's still on your hand. And the other strategy is basically using snatching. So this is analogy to the baby stealing the bottle of milk from the other baby. What you do is you train a policy to perform grasping on your left hand, and then you train a policy for snatching on the right hand. So your policy for grasping should be good enough so that the other hand cannot snatch the bottle from your hand. And on the right is unstable grasping, and on the left is a stable grasping because the other hand cannot steal the bottle from this hand. So this is basically the ideas. We have tried to train these leopards on around tens of objects, and here basically are the results of this grasping. And this is a demo of the results of grasping. And you can see that if we use the baseline without these adversarial agents, the grasping accuracy is actually around 68%. And if you use the adversarial strategies with shaking together, training with the grasping strategy, the accuracy is around 80%. And then snatching is similarly. So as a summary, I have been talking about, in this talk, it's mainly about design different adversarial agents to challenge your target agents. And in object detection, I've talked about occlusion and adding deformation adversaries. And in the robotics scenario, I've been talking about using shaking and snatching strategies. And in the future, I think unclear but an interesting direction will be maybe you can automatically figure out what is the right strategy to design to challenge your target agents. And this is the end of my talk. Thank you.
Questions? If not, let's thank our speaker again.
Thank you.
Our next speaker is Professor Stefano Orman from Stanford. His research is influential in many areas inside and outside machine learning, even including material science and sociology. He also has many papers in adversarial learning, and today he's going to talk about adversarial imitation learning.
All right, great to be here. So today I'll be talking about how to use generative modeling ideas and GAN-style training techniques, not to generate pretty pictures, but to imitate human behaviors in complex environments. Right. So since this is a tutorial, I thought I'll start with a little bit of introduction on what is imitation learning. And so the starting point is reinforcement learning. Reinforcement learning has been, there's been a lot of progress in the last few years, with a number of really, really exciting applications in robotics, playing video games, board games. You probably all heard about the successes in playing chess and Go. And one of the key technical innovations that enabled a lot of these successes is the use of deep neural networks, these very flexible, complex function approximators that you can use to represent these fairly complicated mappings that you need from high-dimensional observation spaces like images to actions. So all of this is very, very exciting, but one limitation is that if you want to use RL to solve a new task, you have to be able to specify a cost signal, a reward signal. Like you have to provide some supervision to your reinforcement learning algorithm, and you need to basically be able to specify what kind of behaviors are desirable and which kind of behaviors are not. So in some scenarios, this is easy to do. If you think about games, you know, the reward or the cost signal is whether you win or you lose. So it's fairly straightforward. But if you think about more complex tasks, like driving an autonomous vehicles, like actually writing down a reward or a cost function explicitly by hand can be actually very, very complicated, right? You want to move forward, but you don't want to move too fast. You don't want to crash into other vehicles. You don't want to go off-road. It can be very, very complicated to explicitly write down the kind of objective function that you want. So in some situations, it might actually be more scalable, more effective to instead provide supervision by using demonstrations. You get to see how an expert performs in this environment, like you see how this autonomous vehicle should be driven on the road, and then you try to learn from that, right? So this is the imitation learning problem. And so basically the problem becomes that of trying to learn a cost function, or maybe perhaps directly learning a policy that can imitate these kind of demonstrations that are provided to you by an expert. And you should think of demonstrations as being a sequence of states and actions that are taken in some kind of Markov decision process. Right, so this is a problem that has a long history, has been studied for a long time. The simplest kind of method that you could use is called behavioral cloning. The idea is fairly simple. What you can do is you can use your trajectories, your demonstrations, to construct a training set of states with the corresponding action that the expert took in those states. And then you can use your favorite supervised learning method, classification or regression if the actions are continuous, and you can try to learn a policy. And that works quite well. In fact, it was used in the late 80s in the first attempts to build autonomous vehicles, using simple neural networks, trying to map camera images to steering actions. It has some limitations. The first one is that small errors can compound over time. The problem is that your learning algorithm is never going to be perfect. It's going to make some small mistakes. These mistakes will lead to you to see states or observations that you haven't seen that are slightly different from the ones you've seen in your training set. And as a result, there's going to be a little bit of covariance shift. You're going to make more mistakes. You're going to see increasingly different kind of like distribution over inputs. So you're going to make more mistakes, and eventually kind of everything will break down. The other problem is that it's kind of like a black box approach where you're not really taking into account the structure of the problem. If you think about typical kind of demonstrations provided by an expert, typically the expert has a goal, the expert is optimizing for something, and this method that just reduces it to basically by brute force supervised learning doesn't really take into account all of the structure. Right, so an alternative approach that actually does take into account this structure, the fact that we're dealing with an MDP and that perhaps there is some kind of objective function that the expert is optimizing for, it's called inverse reinforcement learning. The idea is that we're going to assume that the expert is optimizing for some objective function, and we're going to try to solve an inverse optimization problem. We can think of reinforcement learning as trying to find a policy that minimizes some expected cost. So what we're going to try to do is we're going to try to find a cost function such that if you were to optimize for that by finding the policy that minimizes the cost with respect to that minimizes the cost with respect to that cost function, then you would get back your expert policy pi e. Right? So the setting is like this. We have reinforcement learning. That's an algorithm that takes as input an environment and a cost function. It produces an optimal policy. And then there is the inverse problem, where you start from some demonstrations given to you by an expert, and you try to come up with a cost function that can explain, that can rationalize the behavior. In particular, here we're going to consider a natural formulation of this inverse optimization problem. What we're going to try to do is we're going to try to create a gap between the performance of the expert and the performance of everything else. Like we're going to try to find a cost function such that the expert is sort of like uniquely optimal. It's much better than anything else. One way to formulate this mathematically is to try to solve this optimization problem that you see at the bottom, where we're going to try to maximize this difference of two things, which is the difference between what you can do with any policy and what the expert actually achieves. If you want to make that expression large, what you do is you try to make the second term as small as possible. That term corresponds to the price paid by the expert under that cost. So you're trying to make the cost of the expert very small, and at the same time you try to make the cost of everything else as high as possible. So you're trying to create a gap between the expert and the second best possible thing. So that sort of like you can the expert is sort of like uniquely optimal with respect to the cost function. Now, a natural question is what happens if you try to close the loop? If you start from the trajectories, you come up with a cost function, and then you try to solve a reinforcement learning problem with respect to that cost function. You're going to get an optimal policy, and intuitively you would like this optimal policy to be similar, to correspond in some sense to the demonstrations that you've used as input, right? And so what we're going to do is we're going to try to understand quantitatively what's the relationship between these two objects. And we're going to see that there are some nice connections with existing work in imitation learning and with GAN, right? So in order to do that, we're going to consider a slight variation to the optimization problem we had before, where we're not just trying to maximize the gap between the expert and everything else, but we're going to include a little extra term, psi, which you can think of as a regularizer. It's some kind of preference that you have a priori over possible cost functions. You might specify something like you have a preference towards cost functions that are simple, or maybe you know that the cost functions depend on some particular features. Anything you want, that's a regularizer there that you introduce in your optimization problem. It turns out that this regularizer is actually very, very important because it affects the way in which you measure similarity between the optimal policy that you get up there and the demonstrations that you provided as input, right? So it plays a very, very important role. So the first take-home message is that if we look at this optimal policy pi, this optimal policy defines an object, which we're going to call rho pi. That's an occupancy measure. That's basically the distribution over states and actions that you see when you navigate the environment using this policy pi. Similarly, there's going to be an object called rho pi e. That's the expert's occupancy measure. That's the kind of states and actions that you see when you follow the expert policy. So our result is that when you try to solve this, when you try to combine reinforcement learning with psi-regularized inverse reinforcement learning, implicitly what you're doing is you're trying to solve effectively a generative modeling problem. You're trying to find a policy pi such that rho pi and rho pi e are similar, and similarity is measured by psi star, which is the convex conjugate, the differential dual of psi. So you can see that psi basically plays a very important role because it controls the way in which we measure similarity between these two probability distributions over states and actions, right? So the first takeaway message is that we typically think of inverse reinforcement learning as basically trying to find a cost function such that the expert is uniquely optimal with respect to that cost function. Alternatively, we see that we're effectively solving a generative modeling problem, the kind of problem you solve when you try to train a GAN We're trying to learn a probability distribution over states and actions that is similar to your training data. And crucially, similarity is measured by this regularization term that we introduced in that optimization problem. Right? So let's see some examples just to get some intuition and some connections with existing methods. The simplest case is when we don't use any regularization. We say that psi is a constant, so a priori all cost functions are equally likely, are equally good. Then what is the corresponding psi star? What is the convex conjugate of a constant function? Well, it's going to be something which is infinity unless the argument is 0. So what we're doing is, if we're not regularizing, we're saying that the solution to that optimization problem, to that generative modeling problem, will be a policy pi such that its occupancy measure is identical to the one given by the expert. Now, this might seem like a good thing. The problem is that in practice, we never actually get an infinite amount of data. Right? In practice, you only get so many demonstrations. And so matching the occupancy measure of the expert, which we only have access to through samples, is actually not a good thing. Because what we're doing is we're basically memorizing the training set. We're coming up with a probability distribution which is identical to the training set, which is never what we want to do. This is extreme overfitting. In some sense, we're allowing too much flexibility in the possible cost functions and the possible policies, and so this is not going to work in practice. So one solution is to regularize. The simplest way to do it is to introduce a set of features and, let's say, constrain the possible cost functions to be linear in this set of features. The way to do it is by using a psi, using a regularizer, which is basically going to be infinity unless the cost function is linear in this pre-specified set of features. So we're constraining the possible cost functions to have this special structure. Turns out that if you look at what is the corresponding psi star, this approach will give you apprenticeship learning, which is a method that was introduced about 10 years ago by Peter Abil and Jun-Yan, and where basically the optimization problem that they consider is that of finding pi, finding a policy such that it performs better than the expert over this class of cost functions that are linear in pre-specified features. So we see that if we choose this particular class of regularizers, we get back apprenticeship learning, which is something that worked reasonably well. They managed to fly helicopters using it. But you need to be very, very careful in specifying the right features, right? Unless you get them right, the method might not work. It doesn't give you any guarantee. And intuitively, what's going on is that when you start with your demonstrations and you solve the corresponding inverse reinforcement learning problem, you're basically encoding these demonstrations as a cost function. And then you're decoding back, when you solve the corresponding reinforcement learning problem, a behavior. If your codes are sort of like too restricted, they are only allowed to be linear in these cost functions, then you might not be able to do a good job. This autoencoder is too lossy, and you might not be able to recover a distribution that is similar enough to the input data. So the solution is to use a more expressive class of cost functions. So here we're finally seeing the connection with GANs. It turns out that if you choose this particular regularizer, which seems very complicated, it's based on that expression. You don't need to actually understand what that means. The interesting thing is that if you look at the convex conjugate of that function, the psi star, then you can mathematically show that this corresponds to the optimal negative log loss of the binary classification problem, where we're trying to distinguish between state and actions, generated by pi, by your policy pi, and by the expert. Right? So now you see the connection with GANs. You can see that this psi star basically corresponds to solving this classification problem, where you get to see states and actions produced by the expert. This is training data. You get to see states and actions produced by your policy while navigating the environment with it. You're training a discriminator that is trying to distinguish between true and fake samples, and the loss of that discriminator measures how close these two distributions are. Right? If they are perfectly identical, then the discriminator will have a very, very high loss, and so they will be very similar. Right? So, of course, this is similar to GANs. It's a very, very similar idea. I don't have to go through this because you've heard about it in many previous talks. Effectively, the main difference is that in a GAN, the generator is basically just taking inputs, as input some random noise, mapping them through a neural network, and then producing some sample here. The difference in this approach is that the generator is more complex. The generator has basically two components. There is a policy, which is, let's say, a neural network. It's something that you can train. But then there is the environment, which is something you cannot control. It's fixed. It's given to you. What matters is the distribution over states and actions that you encounter where you navigate the environment using this policy that you can tune. Other than that, it's the same idea. What you're trying to do is you're trying to find a policy such that when you couple it with the environment, you produce a distribution over states and actions that is hard to differentiate from the training data by some kind of discriminator D. So it's a very, very similar idea. The challenge is that training this model is harder. When you have a GAN, so training D is just like in a regular GAN, it's easy. The challenge is how to train P so that you're sort of like going in the direction of fooling P, the discriminator D. Unlike a traditional GAN, the generator is not differentiable. You have this simulator, the environment, which is something you cannot control. You only have black box access to it, but you don't really know how it works, and you cannot backprop directly through it, right? So on the one hand, it's an easier generative modeling task because you don't have to learn the whole thing end to end. You don't have to come up with a big neural network that maps noise into behaviors. Some part of the model is given to you by the environment. On the other hand, it's harder to train because you don't really know how that black box works. Our solution is to basically just do policy gradients over this policy here. The nice thing is that it can be applied to in a model-free way, so you don't really have to understand you don't really need to know how the environment works. It has some good properties in the sense that it converges to local optima. It's also potentially difficult to train, and so our solution, the thing that you actually need to do to get this to work in practice, is to use trust region policy optimization methods. So the idea is that looking at the Euclidean geometry of the space, it doesn't work too well. You really need to think about how much the probability distributions, the relevant probability distributions change as you change the parameters of this policy network, right? So you need to take steps with respect to this kind of trust region defined in terms of KL divergence instead of regular Euclidean geometry, right? So this turns out to work quite well. Here are some examples of the kind of policy that we're able to learn on OpenAI gym environments. So here what we do is we're trying to learn how to control these robots from demonstrations. So we're getting to see how some demonstrations of how these robots perform in the environment, and then we try to learn a policy that controls them and produces behaviors that are indistinguishable from the training data. Another kind of result that we got is on even more complex environments where we're actually trying to work directly from raw visual inputs. So here what we're trying to do is we're getting to see demonstrations on how to drive this vehicle in this driving simulator. And then we're trying to learn a policy. We're trying to learn how to control this vehicle in a way that it produces demonstrations that are difficult, that are hard to distinguish from the training data. And you can see that we're able to learn reasonably well, and the method basically scales up to complex environment, complex dynamics, and very high-dimensional observation spaces. We have a number of other results on kind of standard benchmark tasks. It works much better than apprenticeship learning in the sense that you can get better performance using less samples. How much time do I have? For 10 minutes? Okay, perfect. Okay, great. So I'll want to talk a bit about the other fun things you can do when you take this generative modeling perspective. So what we're doing here is we are thinking of imitation learning as the problem of basically constructing a generative model of these behaviors that we have in the training data, right? And as we discussed before, the interesting thing about this generative model is that unlike a traditional GAN, it has two components. There is something that you can train, and there is something that is kind of fixed, which is basically the environment. Now, this generative model that we have still has some latent variables. And so what we can try to do is we can try to use the latent variables to essentially identify semantically meaningful latent structure in the data, right? So you've seen in previous talks that this is often possible to do it, say, when you have images. When you have images and you train a latent variable generative model, it's often the case that this latent variable Z can be used to discover some semantically meaningful latent structure in the data, like let's say latent factors of variations that are present in the data, and you are able to discover them by training the generative model. And then by, say, interpolating in latent space, you can do things like adding smiles on a face or glasses, things like that, right? Now, the nice thing we can do once we've formulated imitation learning as a generative modeling problem is that we can apply the same idea, not to images, but to behavioral data, right? What we've done using Gale is we've built a generative model over behaviors, and this generative model has latent variables. So what we can try to do is we can try to see whether we can use these latent variables to discover structure in the data in an unsupervised way. So the way we do it is by using an approach similar to InfoGAN. So what we do is we add an additional term to the objective function where we're basically trying to maximize mutual information between the latent variables and the observed behavior. What this does is it kind of like encourages the latent variables to capture the most important, the most salient aspects and factors of variations that you see in the behavior. And one way to think of it is that you can essentially try to cluster and identify different kinds of demonstrations that you might have in the data, and hopefully you're going to be able to do it in an unsupervised way. So kind of like the synthetic experiment is that you might have a point that is moving in the plane, and perhaps the point can take 3 different kinds of trajectories, either this one, the red, or the green, or the blue. But of course, in the training data, you don't get to see, you don't know a priori. This is kind of like a clustering problem. So you don't know a priori that there are 3 different kinds of behaviors in your data. And you can try to discover it using this kind of InfoGale method. By using this maximizing mutual information term, we can effectively try to cluster the trajectories using these latent structures, these latent variables. And we can identify the fact that there are 3 different, if you just train Gale without the mutual information term, well, it has no way of knowing that there are 3 different kinds of demonstrations in the data, and it's kind of like mixing them up all together. If you add the mutual information term, then it figures out that there is variation in the data, it kind of discovers it, and then by controlling, by changing this latent variable, you can force the demonstrations to either be like the red one, or the blue one, or the green one, right? So you're sort of like teasing apart the variation and identifying it using this latent variable. Now, this is a synthetic experiment. A more interesting one is on the driving simulator we had before. What you can do is you can show the model a lot of trajectories in this driving simulator, and then you can try to see what kind of variation you're able to discover in the data. So one of the latent variables that we were able to discover is basically capturing a preference of the driver towards passing on the left or passing on the right. So it turns out that one of these latent variables that we discover by adding this mutual information term is actually capturing whether or not the agent has a preference towards staying on the left or staying on the right. So just like what we were doing before when you're dealing with images, what you can do is you can set these latent variables, say, to 0, and you're going to see behaviors where the agent is actually, let's see if this plays. It's not showing very well. It's always passing on the left, and then when you set it to 1, then you have a preference towards passing on the right. Right? So we were actually able to disentangle this variation in an unsupervised way. All right. Now, the final thing I wanted to talk about is some recent work that we've been doing on extending these ideas to multi-agent environments. So instead of having just one agent interacting in one environment, you might have multiple ones. Like you can see here, there are these 3 red dots that are sort of like chasing the green one. And ideally, we would like to do imitation learning in these more complex settings where there's not just one agent, but let's say multiple agents interacting with each other, right? How can we extend these ideas to these more complicated and more interesting settings? So one challenge with the multi-agent settings is that the problem is that the agents are all interacting with each other, and they could be either competing or they could be cooperating, and we don't really know that, right? And in particular, if the agents are competing with each other, it's possible that the optimal strategy for one agent depends on what the other agents are going to do, right? So there is not a notion of a single optimal way to interact with the environment, because what you do really should depend on what the other agents do in the environment. So what we need to do is we need to change the notion of optimal policy with the notion of essentially a Nash equilibrium, so that which is one way to come up with a solution to this kind of multi-agent setting. The idea is that, let's say that you have a simple game where you have two agents that are either both, they can either drive on the left or the right side of the road. And so, there are kind of like two possible and rational kind of like solutions to this problem. Either they both drive on the left or they both drive on the right. You don't want them to be sort of like crashing into each other. And both are equally good solutions, right? So that's kind of like the challenge that you need to deal with. The way, it turns out that you can develop a theory that is very similar to what we had before, when you can develop an inverse multi-agent reinforcement learning problem. It turns out that there's a very similar kind of like duality theory where you can still view the corresponding problem as an imitation learn, as a generative modeling one, where still this regularizer basically controls the similarity between this probability distribution over states and actions. The final model basically looks like this. It's very similar to a GAN or a GALE, except that now the generator, it doesn't just have a single policy that is interacting with the environment, but you have multiple policies that are multiple agents, which could have different policies that are basically interacting with the environment and then producing kind of like behaviors, producing trajectories. And so we can still train the model, it turns out that if you work out the math, what happens is that now you need to have not just one discriminator, but you need to have multiple discriminators, one for each different agent. One way to think of the discriminator is kind of like playing the role of a reward or a cost function. And so because we have multiple agents, we need to have one cost function for each different one. And the challenge, as usual, is basically how to train the policies so that they together sort of like fool the discriminators. That's challenging because you have to solve a multi-agent reinforcement learning problem, but it's still doable. And we got some pretty good results. Here are some examples of the kind of like input demonstrations. And I have some examples of the kind of policies that we are able to learn using Mihaela. Here is another example where the goal is to kind of go and cover different targets, and the agents have to synchronize because they don't want to go. You don't want to have both agents kind of like go to the same target. And here are some examples of the kind of policies that we're able to learn using our method. So yeah, I think that's pretty much it. I think the key message that I wanted to hopefully get through is this idea that imitation learning is really the same thing as learning a generative model. So a lot of the ideas that have been very, very successful in the generative modeling community, like using GANs, using very flexible kind of like function approximators based on neural networks, they actually translate to this imitation learning setting. And we can actually build these more, I think, interesting kind of generative models where you're not learning everything from scratch. It's not just a big neural network that maps random noise into structured data, but you could have these kind of like hybrid settings where a part of the model is learned from data and a part of the model is actually specified by the user, or maybe it corresponds to an environment. And we can take a lot of the ideas that have been successful in reinforcement learning and we can still use them to train these kind of models. And I think there's a lot of exciting things that we can do when we start thinking about all the advances that we've seen in unsupervised learning for images, audio, text. I think a lot of those ideas can be naturally translated into behavioral data, into demonstrations. We can use these methods to discover structure, do unsupervised learning, semi-supervised learning, transfer learning, and so forth. And that's it. Thank you.
questions?
Yeah. At the time, the thing that doesn't work is if you don't use kind of like natural policy gradient methods. At the time, we were using TRPO, but I believe PPO would work too.
Let's thank our speaker again.
It's my great honor to introduce Carl Wondrich. So Carl is currently a research scientist at Google. He obtained his PhD from MIT, working with Antonio Torralba. And his research focuses on learning without human supervision and transferring knowledge between tasks and modalities. So he will join Columbia University as an assistant. Let's welcome Carl.
Okay, hello everyone. So by a show of hands, how many times have you had technology fail on you? Really? Okay, there's more hands going up. Okay, so one, sometimes maybe you're watching a video, and your video codec just completely, dies. And so, maybe in the beginning of the video, you're watching in color, and all of a sudden the color disappears, right? And now you're left with this crisis of, what color is that? What color is that pixel there? And you guys are all smart people. What color do you think that arrow is pointing to? You can shout it out. Red? Everyone thinks red? Does anyone not think red? Oh, there's some people thinking no. So the reason why, right, you all are predicting, or most of you at least, are predicting that this is red, is that you know that color is generally temporally coherent. And that, it would be very weird if that boy, if his shirt were to suddenly change to red, right? Or change to green. And so, what this slide is showing is just to make this point that, generally, if you just download a random video from the web, there's this natural coherency of color. And there's obvious exceptions to this rule. Like you can turn on a green light and all the colors are going to change. There's several illusions where this isn't true. And there's also color constancy effects. But generally, if you just take a random video from the web, the color is going to be fairly coherent. And so what we've been trying to capitalize on this natural coherency of color in order to train models for self-supervised tracking from unlabeled video. And kind of the main idea here is that we want to train models that can colorize grayscale video by copying colors from this reference frame. And what we're going to show is that this causes tracking to emerge automatically from this proxy task. So I want to take a step back and just, I think what's very important about this work is that, what's important about tracking is that it's going to let us envision go beyond just operating on video as a bag of frames, right? For if we want to try to predict what's going to happen next or recognize human activities, we need to link things through time. And we need models that are able to track. And so I think that researching this question of how do we build self-supervised models for tracking is going to be very important. So the idea of using colorization is not new by any means. There's several works in the community that are trying to capitalize on this signal for learning representations. For the most part, they've focused on trying to colorize a single frame. And so what we're going to do is what makes us different is what we are trying to do this in video, and we're going to show that tracking comes out. So we're not going to be answering this question just, what color is this? We're not trying to say, let's synthesize a new color. What we're going to ask instead is, where should we copy this color from? And so to make this point clear, I thought we could play a little game. Okay, so can you all see my cursor? Yes? Okay. So what I'm going to do is I'm going to move this cursor around. And what I want you to do is clap when you think the cursor is covering over the, is on top of a region that you want to copy the color from. Okay, does that make sense? So just as a warm-up, can everyone clap as a cheap applause? No, like a loud clap. Okay, good. All right. So think in your head, where should this cursor go? Right? Just kind of think mentally, where in this image here should it be? Right? And I'm just going to move it around. What is that? Somewhere in the rug. You want to clap here? Why don't you clap? Okay, good. So, you all took the safe option here, except you. Right? You understood about instances and that where should you copy this color? Well, is from the same person, right? You could have gotten lucky though, right? And actually clapped when we were hovering over the towel, right? But you didn't because you wanted to be safe, right? And so this is an intuition that we want to encode in this model, is that let's learn to track by copying colors from the safest location. All right, here's another example. This one's a little hard. Where do you guys think we should copy it from? You can shout out your guess. Was it? Here? So it's hard, right? Because actually, the point we're pointing to in the red arrow is occluded now, right? There's no valid correspondence here where we should copy from. But color is generally robust to occlusion, especially self-occlusion. And so this is a strength of using colorization as a signal for learning to track, is that we can be robust to these fairly complex transformations. Okay, so to be a little more concrete about this, we're going to try to train a model to colorize a grayscale frame, for example, here. And the way it's going to work is we're going to train a pointer and showing this solid yellow arrow here to point into a reference frame, such that wherever we point, we can look down and copy the color that corresponds to, right, and drag it back. So to formalize this more, we can say what we can do is we can embed each pixel in this network with a convolutional net. And we're going to write this low-dimensional embedding for each pixel as fj in the input frame and fi in the reference frame. And then we're going to define a similarity metric in this embedding space between fi and fj as aij. Okay? Now, to get this idea of let's pick the safe option, right? What we're going to do is we're going to try to force this pointer to only point to one location, right? We don't want it pointing to all these different locations, because that would just do something similar to clustering on color. We don't want to cluster on color. We want to point to the safe area where we can grab the color from. And one simple way of trying to encode this intuition is just using softmax. So we can, as a similarity metric, we can take the inner product between these embeddings and compute the softmax such that these rows sum to 1. Then, what we can, for our predicted color, for what we think the color of fj is we can just write it as a weighted combination of all the colors in the reference frame weighted by this matrix aij. And so our final loss will just be trying to predict what the target color CJ should be, right, by learning what this weighted combination should be, which you can interpret as a pointer. So here's a couple of examples. On videos that this model didn't see during training, we trained this just on massive amounts of unlabeled video. We used the kinetics data set, but discard the labels. And here's some videos from the validation set. So the left frame is showing what the reference frame is that has the color. The middle is showing the grayscale video, and the right is what our predictions are. You can see it's fairly good at capturing some complex transformations, like as the people turn around and they self-occlude, right? This will get colorization, or as the eggs move around on the pan. This would be a pretty challenging case for something like optic flow. You can also see some failure cases. For example, the woman's legs, they appear in the future, but they're not actually in the reference frame, so we don't get the color right. Here's a few more examples. It's funny when you start thinking that butter spreading on toast is a really complex example, but what's the valid flow field here, right? As butter is starting to deform, it's really hard to find exact correspondence, but color is kind of an appropriate amount of coarseness that we can propagate the colors. And so what we think is that because the model is able to solve this colorization task, that internally it's learning this mechanism for tracking. And so to actually explore that further, what we can do is just train this model on unlabeled video, and then at test time, we don't do any additional training. We just, instead of propagating colors, we can propagate masks or key points. And use this as a way to track a region of interest. So here's a couple of examples on videos that's not seen yet. Only the first frame is given, and the model is propagating it forwards. The colors are corresponding to different instances. And so the key point I want to underscore here is that this model was never trained for tracking. It never even saw a segmentation task. All it was trained to do is colorize video, but we can repurpose it without any additional fine-tuning for tracking. And it works in, I'd say reasonably complex situations. So for example, the ball in the bottom right undergoes an occlusion by the tree, right? And we're still able to track there. Even if multiple objects or people have the same color, it's able to do the tracking. So for example, the first row, the first and second column, right? Both people are wearing these white jerseys or jackets, and the model is able to actually to distinguish between them. And kind of the intuition there is right. This model is trying to pick the safest region to point to, because this is a tutorial on adversarial learning, right? I guess you could say that like it wants to avoid the adversarial situation where there could be a color that changes. Okay, so here's a few more results. It does a reasonable job at fairly complex transformations. It's not perfect by any means. But what's cool is that this model is fairly versatile. And so we can use it for different tracking tasks without even retraining. So here's an example where we use this for tracking human pose or key points. So here just the first frame is labeled with the human skeleton, with labeled as different key points, and the model is trying to propagate this forwards. To quantitatively evaluate this, we can look at a plot where the vertical axis is showing our average performance, and the horizontal axis is showing the time into the video. So what we're going to expect is that as the video goes further out into the future, performance is going to get worse. The simplest baseline you can think of is let's just take the first frame that's given to us and repeat it throughout the entire video, right? And that doesn't do very well. We compare against kind of the state of the art in optic flow. This is trained on, this is FloNet 2.0. It's trained on a large synthetic data set of flying chairs. And so, you can call it self-supervised because there's no labeled data. It's all generated with static engine. And so that model does better than the identity baseline. Finally, what our result is showing is on the red curve, which is from colorization. And so what this is showing is that the model is starting to learn to track better than the latest methods based on optic flow. And I think what's cool about this is that we never actually told it to tracking, right? It's just emerging automatically from this colorization model. We can break down the performance more by different types of attributes in the video. The one I want to bring your attention to is the dynamic background, which is a case where we know optic flow typically performs poorly. But the colorization model, because it's trained on so much data, right, it's actually able to learn to be robust to these types of artifacts. One way we can gain insight into the model as to what it's learning is we can take these embeddings and we can project them down into 3D dimensions using something like PCA, and then just visualize this as an RGB video. And so what this is showing is that pixels that have similar color in this visualization are going to be close in embedding space. And so what this is suggesting is that this model is starting to learn to embed objects, right, that correspond to the same instance into a similar region in the embedding space. So I want to draw an analogy to some work that we did, I guess, like a long time ago now, which was trying to generate videos with GANs. And I guess that's the reason why I'm here, so I have to show this slide. And so right here, what we're trying to do was learn these models on to generate video, either from noise or conditioned on the past to actually like predict videos into the future. So what we're doing with colorization here is actually pretty similar. We're trying to predict the color into the future. It's just that we're seeded with the grayscale frame. And so I think that as we start to improve these methods for future prediction or colorization, we're going to start to see these improvements in these other tasks. So what we found in this colorization work is that the errors, we found that when the model when the model fails to colorize a video, that is often correlated with the failure to track. And so the colorization coefficients in our paper, I don't remember what it is anymore, but it was fairly high. And so what this is suggesting is that there's still lots of juice left in this colorization signal for learning to track. So I think that as we start to, if you can improve these models, maybe you can use a GAN to improve colorization models, that we'll see these improvements in downstream tracking. I forgot to mention that we don't outperform the supervised approaches in tracking yet. I think that's okay because these methods are trained with massive amounts of labeled data. It's like ImageNet and COCO and some other data sets. And so the main point here is, can we learn to colorize? Can we learn to track without any labeled data? How much time do we have? 10 minutes? Okay. Okay, so kind of broadly what we're interested in is trying to build visual models that just learn from massive amounts of unlabeled video. And I think this is a promising direction because videos are rich. There's lots of context, whether it's color or across time or even across modalities like sound, that we can use for learning. Now, it's not a it's not going to be as powerful as for example, as a method that learns actively, right? But the advantage of learning from passive video is that we can scale up very efficiently, right? It's just computation at this point. So one direction that we've also been using for learning from video has been trying to transfer across modalities, for example, between sound and vision. And so, we're at CVPR where we often work on tasks like trying to recognize an object from an image. In the sound community, there's a corresponding task which is trying to recognize objects and scenes just from sound. This problem has typically been hard because it's difficult to collect a huge labeled data set for sound. And so, in some work led by Yusuf Aitar, what we were showing was that we can essentially train a student model in the sound domain in order to recognize objects where vision is the teacher. So you're learning to hear by seeing the world. And so this is very scalable because we have access to huge amounts of video that have both vision and sound, and they're naturally synchronized. That we can transfer visual knowledge into the sound domain without any additional supervision. So I wanted to show you a couple results. I'm going to play a video, but these predictions are only coming from sound. There's no vision used here. And so the top is showing our predicted scene categories from sound, and the bottom is showing predicted object categories from sound. And so as I play the video will fade in. try to think if you think these predictions are correct. Let's hope the sound works.
Good one. Oh, busy boy.
So what's cool about this is that the model's never seen a labeled example of sound, right? It's trained with lots of labeled data from vision, but we can transfer this naturally into the sound domain. Here's another example. The top is scene categories that are predicted from sound. The bottom are object categories that are predicted from sound.
Dear Gordy, happy birthday to you. Hey!
All right, so candles don't make any noise, right? But the model's seen enough happy birthday songs and birthday cakes that's learned this correlation, right, between the happy birthday song and candles to predict that. What we've recently been trying to do is go beyond just trying to recognize what's happening inside a waveform to actually trying to ground where the sound is coming from in the video. So we might have a video like this, which has two different sources of sound. And what we've been developing is an approach where you can essentially take your cursor and click on a particular region in the video, and it's going to play the sound that the model thinks is coming just from that source. And so this is a result. I'll show you the result. And this is being synthesized just as where the input is the mono sound you just heard. So if we click here, of course, if we click on the tuba, I guess, I don't know, we can hear that one instead. So if you're ever at a party and someone is playing a music on an instrument, you can mute them, right? And of course, if we just click on the back wall, you don't hear anything at all. This same model is able to additionally predict the sound volume, saying which pixel is producing the volume, is kind of estimating the amount of sound energy coming from there. And we can also cluster the embeddings to separate these two sounds visually in an unsupervised way. So this is work that's been led by Heng Zhao at MIT. And what he's been developing is exactly this, is a model that takes in a short video clip and the mono sound, and is kind of how to place those sound sources locally, localize them into the video clip. This has become a really hot topic in the last 6 months, with several works exploring a similar idea of trying to source separation with vision and sound. I've listed just a few here. All of them have a different approach and work in different situations, different advantages and disadvantages. So it's cool that there's been a huge diversity in methods. So the way ours works is we're going to try to just use massive amounts of unlabeled video for doing this source separation. And the key insight we're going to take advantage of is that sound is approximately additive. And so if we have just these random videos, we can play each one. And since it's additive, what we can do is we can just combine all of them together. And what you hear is this kind of jumbled sound like this. So what we want to do now that we have this jumbled sound, which we can get essentially for free, we want to train a model that tries to go backwards. It tries to take this jumbled sound and recover the original components. This problem by itself is ill-posed. There's many possible ways you could try to separate these into different sources. And so what we think is that vision can come to the rescue and make this problem more well-defined. And so what we're going to design is a model that is going to take in both the video clip and the jumbled sound, shown on green here, and it's going to try to recover just the sound coming from that clip, right? So green is going to have multiple sounds from multiple videos, and network is going to have to learn to separate out the original sound corresponding to the video. And this is easy to do because we know where what video the sounds came from. You have to go into the paper to see the full details. I'll give you the high-level idea here. We're going to have a network we're going to call the video analysis network. It takes in the video and is going to try to estimate k different coefficients. We're also going to have an audio analysis network that's going to take in the waveform, and it's going to predict k different channels. And so what our intention is that the audio network here should learn to separate the sounds so that the vision network can select which channels it wants to use to combine back together. And that's what you're showing here. So here I'll just show a few more results and we can finish. So here's another one where I'll play the mixed sounds. We can take our cursor and click on the sax, and we'll hear just that. Or if you really like guitar, we can just listen to that. All right, and of course the wall, you don't hear anything at all. Just as proof. Okay, so you can use this for different things. Like the model is kind of is versatile for, as you're saying, is for estimating the volume or trying to cluster the sounds into trying to cluster the sounds and ground them in vision. I'll end with an example where the final demo is what we can do is we can adjust the volume of different sources. So if you're ever at a concert and you just want to mute someone, or you want to like make your friend louder, you can use this system. All right, thanks very much. Oh yeah, that's a good question. We've not tried to do that. There's been some work by Andrew Owens that does do that. So I think there's probably a way, but Andrew's the guy who's done it. So. Okay, thank you.
So I have the pleasure of introducing Alyosha Evros for our last talk. Alyosha has been really one of the main forces behind a lot of the work that you saw today. A lot of it came out of his lab at Berkeley. And I think it's really no surprise. Alyosha has been working on generating realistic images since way before most of us thought that generative modeling was even a thing, was even possible. Back around 2000, he was making realistic textures, and he was also acting, I think, as a really good discriminator, not just a generator, but I found this out when I was working in his lab, and I'd make slides, and if anything was slightly misaligned, he would notice it. If colors weren't saturated and weren't quite the right color, he would notice it. So he's really good at noticing artifacts and what is unrealistic in images. I think he's also really good at discriminating between good and bad ideas and identifying big, good ideas. So a couple of years ago, two of the big ideas that he was pushing in the lab were GANs. He had identified that as being important. And also cycle consistency. And there were different people in the lab working on these two different topics. Some people were working on cycle consistent like tracking and correspondence models, others working on GANs. But we all kind of knew that, well, these were the two big ideas. There's got to be, if you did some kind of cycle consistent GAN, that would be good. We had no idea what that would mean, but we knew that that would be a good idea. And Alyosha was just constantly kind of telling us, yes, there's something there. There's something to do with cycle consistency, something with GANs. And of course, it did turn out to be a cool idea. So I think Alyosha is going to tell us a few more big ideas now, and hopefully we can learn something. So let's welcome Alyosha.
Thank you very much for this introduction. I have nothing to do with any of this. It's of course all the students and the postdocs, and I'm just complaining about various things. And so I thought that I should stop from the complaining, and let's just double check that the audio is going to work. How do I test it? Oh, I can test this. Hold on. Okay. Very good. Okay. So, yeah. So I was asked to kind of try to do like a summary of this tutorial, and to kind of look at where are we with GANs, and I can't really speak for anyone, so it's going to be a very personal reason why I think GANs are cool and why I love GANs, and kind of we can have this as a departure point, and then maybe have some discussion at the end with all the other speakers. But of course, before you declare your love for something, you have to first be sure that that you're not being just infatuated, that you also know the downsides. And so here I first list the reasons I think, that legitimate reasons to dislike GANs. Okay, and those I'm sure you have heard some of them before, but I think it's kind of nice to enumerate them. GANs are a devil to train. Don't let anyone convince you otherwise. They are very hard to get working. You really need to have the magic in your fingers to get them to work, right? And also weird things happen when you train your GANs, right? So GANs are supposed to, you're supposed to get this Nash, equilibrium. The discriminator is supposed to lose, the generator is supposed to win, and that's where you get the beautiful solution. Of course, except what happens is that the discriminator nearly always wins. The discriminator, it's easier to be the discriminator. The discriminator still always wins. And you would think that that would mean that this shouldn't work. And yet, somehow, we still get nice pictures and good results. So this is a mystery. It's not actually, the optimization is not really doing what we want it to do, and yet it seems to be working. Okay? Another annoying thing, sometimes training longer makes things worse, right? This is not what you want to hear from a machine learning algorithm, right? Sometimes it's important to stop at the right time, otherwise your results are going to get worse. Not really a nice feature, okay? Even worse, sometimes more data doesn't make things better. For me, as a data-driven fanatic, this hurts, right? You add, 10 times more data, and things don't improve. Sometimes they might even get a little bit worse. So these are all issues that are still present, and if any of you know how to address them, I think this will be great. Now, kind of more generally, if you pick any given problem that you want to solve, some application-tailored solution will probably work better. Okay? GANs are really, the beauty of GANs is in their generality. That it's this hammer that you just, everything looks like a nail with this hammer, right? And they're general and they can be applied to many different things. But if you're really only solving one problem, probably just doing a more application-tailored approach will probably be a better thing for you. It will be easier to train. You will probably get as good or better results. Okay? Now, of course, once you kind of produce a solution, it might not translate easily to something else. But if you only have one thing to do, then maybe this is a fine thing. An example recently is this the use of the perceptual losses from the Gaddis paper, as used by Johnson, for example. Instead of GANs for image generation, you basically just use a loss based on the gram matrix of your features of a trained network, and you get surprisingly good results for a set of tasks. For example, for the labels to cityscape images, this works surprisingly well. For things where you have more complex multimodal data, doesn't seem to work as well. But if you know your task, try the simple things first before embarking on the miserable, painful training the GAN train. Okay. Finally, as you already heard today, it's not even clear that they're really a generative model. Do they really generate a distribution? Could it be that they're just fancy data memorizers? There is definitely some evidence to point to that direction. You have heard some earlier today, and there is some more around. So these are all things, kind of notes of caution that you need to know before you embark on the GAN train. Oh, sorry, I have an example. So the data memorizer example is very nicely illustrated in a very nice work. I'm not trying to diss this at all. This is a fantastic work from Keras et al. In iClear this year, where they basically use the GAN to generate use beautiful random faces. This is just a random walk in the feature space of faces. Okay, just beautiful thing, right? But if you look at the same approach, working on scenes, you immediately see that basically it's kind of just jumping from one memorized image to another memorized image, and the interpolation between those, it's not really that exciting, right? And why is this happening? Well, faces, and they also align the faces very nicely. And faces, we know that faces form a nice linear subspace, and so interpolation in face space, does look good. Whereas interpolating between scenes, who knows what that even means, right? So this is kind of an example, another kind of example of that, the whole, generative in the GAN, in the generative adversarial networks is, maybe should be taken with a grain of salt, okay? And yet, I still love GANs. I think GANs are wonderful. Last time I gave this talk, I had 3 reasons I love GANs. I have 2 more reasons, okay? So the love is ever growing. So what are the reasons? The first reason is that GANs set up an arms race. Second reason, GANs can be viewed as a learned loss function. And Phillip, I think, already talked about that. GANs can be thought as meta-supervisors. GANs are great data memorizers. I love the fact that they're memorizing. I think that's it's a feature, not a bug. And finally, GANs are actually on the way to democratizing computer art, and are used as tools by real artists. Okay, so I'm going to go through these 5 very quickly. So arms races. Let me start from a long time ago. I was born in the Soviet Union. Late 80s were not good time in the Soviet Union. There was no food. There were lines everywhere. You go to the store after you stand in this line, and there is nothing in there. And then we immigrated to the United States. I went to the supermarket, and my God, look at this. And to me, this was a big shock, right? And I also felt very bad because, we Russians, we're not stupid, right? I mean, there are great mathematicians, physicists, writers, philosophers, we know how to do stuff. Why is it that we can't get stupid, food inside of stores, right? And I thought about this for a long time and read some, read books about it, and it seems that one of the fundamental obstacles is that in the Soviet Union we had this idea that's called the 5-year plan, where you set up a goal, right? You write your loss function 5 years ahead, and you say, okay, in 5 years, we are going to manufacture that many hamburgers and that many shoes, and then you just follow that goal no matter what, right? And to explain to you why this is a bad idea, here is an example. This is an HP calculator, HP 80, a famous pocket calculator, 1973. And here is the Soviet version, about the same time, of a not-so-pocket calculator, right? Why did this happen, right? Why were, Soviet pocket calculators the biggest pocket calculators ever? Because pocket calculators, it wasn't a goal. Nobody set up a goal. Nobody wrote a loss function. Let's make a small calculator. No. Calculators were these big machines, cash registers, and the idea was that you compute with them, right? They were computational devices, right? And they were big. They were, in the 40s and 50s, they're that big. So how did we get to the pocket calculator from there? Well, not quite clear, but it seems like what happened is that, HP is in a competitive environment. It's an arms race with a bunch of other manufacturers. It needs to get its product to be cheaper. When you have a big, ginormous machine, it's expensive because there is a lot of metal in it. So what do? You try to make it cheaper. By making it cheaper, you make it a little bit smaller. Okay? Then the competitor makes it a little bit smaller again. Okay, then you say, oh, can I make it even smaller, right? And so you're fighting with everyone to make your thing cheaper and smaller, and then at some magical point you say, oh, wait a minute, look at this. I can almost fit it inside of my pocket. And there you go. You have emergent properties that are just the cause of the arms race. They were never part of the actual initial goal, right? That wasn't what HP was optimizing for initially. It just emerged as part of the arms race, okay? And the fact that the GANs are intrinsically have this arms race mentality in them, I think is a really great idea, because they are able to create things that, a stable loss, 5-year plan loss function is not going to foresee. And this is why I think that this is actually just the beginning, that I think we'll see much more of this type of setting up arms races, because that's how we're going to get cool new things to emerge, and not just to optimize the things we already know, right? Because what we want is we want something new to be created, and GANs is, I think, a great first step towards this. Okay. 2, GANs as loss functions. I'm just doing a point to the slide that Phil already talked about. You can think of the discriminator in a conditional GAN as basically a loss function. It's quite a loss function, but you can just think about it as a loss function from the perspective of the generator, right? So you basically, instead of saying, okay, this is L1 or L2, you're going to basically learn the loss function from the data. So this is kind of connected to this idea that something is going to emerge that you did not have to specify a priori. And I think that's a very neat thing. Okay? Number 3, GANs as meta supervision. So meta supervision is a little bit of a new term that we kind of adopted in Berkeley. So let me explain a little bit. So there is direct supervision. This is your standard direct, machine learning. You say, okay, I want f of x to be equal to this label y for millions of xy pairs, right? And I'm optimizing for f that will do this for me, right? This is basically like you are, you're in college, and you goofed off the whole semester, and then tomorrow is the final exam, and you don't know anything, so you get like all the old exams, and you're just going to memorize question, answer, question, answer, question, answer, question, answer, right? And guess what? It actually works, because the professors are lazy. The new exam is going to be probably very similar to the previous exams. I did this myself, so you're gonna do pretty well on the test case, on the test set, but you haven't really learned the material, have you? I know I haven't, right? So this kind of direct supervision is basically just asking you to memorize. It's the natural thing to do. It's just memorize these pairs, right? Whereas, of course, the right thing to do is, you actually do the work. You say, okay, this is my, this is my problem. I try to do the problem, and then only once I do the problem, I go to the back of the book and compare it with the answer, something like this, right? So that's where direct supervision is in my mind, very problematic. It allows you to cheat. In fact, it cheating is the right thing to do under this setup. Okay? And so if you look at what the GANs do, right, the GANs are not really directly supervising what the answer should be. They're kind of meta-supervising how the answer should behave, right? So your standard discriminative loss here is basically says, I want f of x to be in the set y, in the domain y, right? I'm not going to tell you what it should be. I just want it to be in the domain of correct solutions, right? It's a much less, it's not very, you get much more freedom, and because you get much more freedom, you need to work harder, okay? And so the idea of just kind of giving you the freedom and making you work harder suggests that GANs might allow us to train models that are hopefully less likely to overfit and more likely to generalize, we hope. Okay? So this is, and other things are an example of meta supervision. For example, we talked about cycle consistency, right? That's another example of meta supervision. You're just going to say, I don't know what f of x should be, but I know that g of f of x, better be x, right? Something like that. So again, you give it more freedom, and because you give it more freedom, hopefully it's going to learn more rather than memorize. Okay? And there's plenty of other type of meta supervision tasks that I think are possible, and I think it will be exciting to try to discover them. Okay? 4, GANs as compositional parametric data memorizer. So before most of you guys were born, back in the 90s, people generated images, and believe it or not, they actually looked pretty good. And the way we did it was very simple. We just randomly picked pieces, or maybe not randomly, picked pieces from the source and put them together and made sure that the boundaries were okay. And it looked okay. Okay? For those of you who weren't born yet, it's kind of, imagine it's like pixel CNN 20 years earlier, right? Without the CNNs. Right? And this was applied to things like image analogies, Aaron Hertzman stuff, where because A is to A prime as B is to what, and then you basically again just copy pixels over and you get good pictures. Okay? And the power here was the power of the data. The data, the copying, stealing the data, and putting it together in new ways was the way that we were able to create good pictures. Okay? And if you've seen yesterday, I think, there was the battle between two wonderful papers, right? One paper in the same session, right? The Pix-to-Pix HD paper that has beautiful results doing Pix-to-Pix with high resolution and very, very nicely done. And the other paper was basically doing a version of nearest neighbor, no GANs, and basically also getting very impressive results. Okay? And so kind of the naysayers say, okay, why do you need GANs? You have all these pixels. It's basically we should just go back, where we came from 20 years back and just steal pixels and it will be fine. Okay? I think there is definitely something to that. I think if you just steal pixels the right way, it would be fine. You would do very, very well. But it's kind of hard to figure out how to steal pixels, and it's also very time consuming. My old work on data-driven image synthesis, it would take a week to generate an image, right? Because, non-parametric searching for nearest neighbors is a slow thing. And so even if GANs aren't really generative, and even if they don't really capture true distribution, I don't care. They are amazing data memorizers, and they are way, way faster than doing it not parametrically. They are just as good, but really fast. So I'm a big fan of nearest neighbors, and I'm sold. These things, they can memorize huge amount of data, and they can retrieve it like on constant time. It's really amazing. Okay, even better. It's doing some kind of a magic where, when we were doing this patch-based texture synthesis and other things like that, the key was to figure out exactly the size of the patch. How much do you steal? You steal too little, it doesn't look good. You steal too much, and you basically have all these boundaries, and it doesn't look good again. And GANs seem to basically figure out how much to steal from the training data. And so in a way, they're kind of like compositional nearest neighbors. Now, maybe they're doing more than nearest neighbors, but at least they are very cool compositional nearest neighbors. So to me, this is a great thing. It may be not what what the machine learning people want with all of their nice distribution matching and stuff, but I think practically as a way of injecting huge amount of data and then using the data, this is quite a cool method. Okay. Finally, GANs as a new artistic tool. So when we published our work in this space, my co-authors Jun-Yan and Phil and Tae convinced me that we should just release everything online. Not even like just for anyone. For profit, not for profit, who cares? So we just put everything on GitHub, and kind of a magical thing happened, even within like a couple of weeks. People started using this software, and they started posting the results on Twitter, and the cool thing was that a lot of the people who were doing this, they were not computer scientists. They were just random people, or they were actual artists. And over the months, all this Twitter feed was full of this really cool and creative approaches of using GANs for artistic purposes. And of course, pretty soon, the main purpose of the internet was revealed to us when Chris Hesse produced an app that basically uses the Pix2Pix software to create cats, and then things just went really crazy. But crazy in a kind of a cool, creative way. It seems to have touched a nerve somehow, that it unleashed something in the population, and even the great Jan LeCun was not immune to trying his hand at some of this thing. All right, but I think the later on, more serious artists have also gotten into the action. So here I'm just going to put a whole bunch of links here that we found, and the slides will be available. But I'll just show you a couple of examples that we thought are particularly cool. So for example, this is a work by Elena Sarin, who is an artist, and the way she uses GANs is really interesting. So she's an artist, and she draws. So what she does is she draws a sketch, and then she trains a GAN on her prior work, and then uses it to colorize her sketches. And in fact, she posts how her process on this tweet, and it's really nice. She says, my watercolor teacher used to say, let the medium do it. Like for watercolors, basically, you want to let the water and the paint kind of do its own thing. You let it be. You just wait to see what happens, right? You don't want to control it too much. And so basically what she's saying, true that. So my sketch provides the foundation, and the network does the thing. I don't fight, just constantly tweak the brush GAN toolbox, right? So she coins this term, brush GAN, right? So it's not like the GANs are replacing the artist. No, the GANs are just a brush, another brush for the artists to use. And I think this is really cool, because this is it's democratizing, a fairly complicated mathematical machinery that basically anyone with a GPU can just download and use it. Finally, I will end on one of my favorite examples of using GANs for an artistic purpose. Let's see if it works. Okay, so this artist, Memo Acton, is a wonderful artist. I highly recommend that you go to his website and see more of his creation. This is it for us here. Thank you very much. So before we finish, though, I think it would be nice to maybe have, for those who don't need to rush to the airport, to actually also have a little, end of the tutorial question answer session with all of the speakers, maybe we can raise some of the kind of more philosophical questions here. So maybe can all the speakers that are still around come over here, and we can do a little. I can do the MC for any of the questions that were still. So, questions. Explain everything. And are we going to have GANs in 5 years? Or is it going to be something new?
I mean, I'm surprised that GANs have lasted as long as they have. Usually generative models last for like months to a few years and then get obsolete. So I really can't say where we'll be in 5 years. I wrote the deep learning book. MIT Press asked me if I'd like to write a book on GANs, and I said, not right now, because I don't know if they'll last long enough for that to make sense. So it would be exciting if they last that long, but it would also be exciting if we got something better.
So as a media, we find a lot of application of GAN for content creation, video game, media. So what I can say is we will try to make it survive for the next 5 years.
For Ian's book to make some money.
Yes.
Do we have any questions from microphones? I can't see anything. Jun-Yan, do you see it?
CVPR questions are really tame compared to NIPS questions.
Oh, I think this is a challenge.
Oh, it's not a complaint. NIPS questions can be more of accusations, if people know what story I'm talking about.
I see we got a question.
Okay. So you talk about the memorization thing. So the fact that we saw, for example, in the progressive GANs that seeing things. So I'm just wondering, when you see GAN papers, you see a lot of measures like inception scores and FID. So just wondering why we don't see measures which try to analyze how much of that is happening. So how much of that memorization or overfitting is in fact happening in those existing GANs measures that we see. So
I think there are measures. Ian or Jun-Yan, do you want to?
Maybe Sanjeev?
Sanjeev, yeah.
Yeah, but it's not an automated measure, right? The birth rate paradox. Yeah, in my talk I suggested this birth rate paradox measure, but it's not automated. I guess you could, we haven't done it, but somebody could try to come with automated analogs of that. That would be a good project.
Or like lots of money with Amazon Turk.
Right.
Get Amazon to sponsor this.
Yeah, so I have spent a few months working on GAN measurement, but didn't succeed very well. And I mean, and I graduated, so I don't need to do anything about that. But I feel like the measurement should be non-differentiable. So otherwise, you don't need GANs anymore. But, so either it's probably like very hard to compute. You can only sample. So you can only do it by sampling. It's very slow or whatever. Otherwise, you just optimize that measurement directly, and probably so you either have GANs or you don't have GANs measurement. So that might be contradicts each other.
it's just that I can imagine the best possible GANs that just takes randomly a photo from the training distribution, giving it out, and we'll get a perfect FID and inception score. So just wondering why we don't have some measure of that will capture that.
So as far as I'm concerned, this is actually fine. Just memorizing the training set, if it's like gazillions of images, that to me is already a very cool thing. But I think people are working on this. It's a hard problem.
So at the previous GAN tutorial that Mihaela and I organized at ICCV, one of our invited speakers was Lucas Theas, and he did his whole talk on evaluation, and he basically just said, pick a downstream task that you want to use your model for, and evaluate based on the downstream task. Like if you want likelihood to do like anomaly detection or compression, measure your compression rate, measure your test likelihood, which is possible for some architectures of GANs. If you want pretty pictures, have mechanical Turk users rate the quality of the pictures, or have a more controlled setup where people evaluate the pictures in controlled perceptual lab settings. It's kind of a common theme in machine learning that for a lot of areas like fairness and reinforcement learning, evaluation has actually become hard in those areas too. And the answer usually seems to be evaluate on a downstream task. And that's maybe not the best that you can do for debugging individual components, but it's the best you can do for knowing that your metric is actually meaningful.
Okay, thanks.
So one of the things that struck me is, in the last 6 months or a year, GANs have gone from sort of a neat tool and a way to generate pretty pictures to now you're seeing a lot of more practical applications based on some of the ideas, like a lot of the domain adversarial approaches we've seen. What do you see coming down the pipe next for sort of more practical applications of GANs or those ideas?
Picking just one thing, the thing that I've hoped people would do with GANs the most is model-based optimization. We see this a little bit with, for example, the crowns made by Glidewell Dentistry, where they use GANs to model toothiness and then search over the space of teeth to find the one that fits you. But I would like to see GANs coming into the physical world a lot more. I'm surprised that fashion wasn't actually the first place we saw this happen. It's maybe not as important as medicine, but it also seems just like easier to close the loop with less regulation and so on. Just imagine making GANs that make every kind of clothing and accessory that appeals to you the most and actually fits you too. I'm surprised people are not doing that yet.
Thank you.
I think that image forensics and video forensics is an exciting direction where GANs could really be very useful as a proxy for the bad guys. I think that's going to be happening soon. Thanks.
Hello. It's interesting to think of GANs in terms of data memorizers in a good way for, say, creative applications. Do you think, it might be a stupid question, but do you think this fact that they are kind of a data memorizer can be used for stabilizing GANs in some way, maybe using combining some old techniques with these new?
Well, I guess that was the aim of my talk. This is how we started looking at merging maximum likelihood with GANs. But we actually saw that in practice, this destabilization of GANs and this mode collapse of GANs actually leaks into the hybrids as well. And with these new GANs, like self-attention GAN and so on, there's not that much application, I think, in my opinion, for these things right now.
Thank you.
Hi. Alyosha showed some really interesting examples of artists using GANs for some creative applications. I'd like to point out that tweaking GAN parameters is not exactly an intuitive interaction, and it also, in a sense, while democratizing art for maybe people who can draw, it also restricts access to these high-tech applications for, well, most of the artists, actually. So I guess my question is, do you think it is important for us to make a bit more of an effort to incorporate user interaction into some of these artistic applications of technology?
So I think this is a very fair point. And I think in a sense, the artists, they do want things to be hard. You know, the creative process is about placing restrictions. Why would you write poetry? It's much harder than prose. You need to make things rhyme, and yet these restrictions give you this artistic avenue for artistic expression. So I think in that particular case, tweaking the parameters was something that was part of the artistic process. But I think for kind of a broader range of, maybe non-artists, but just people who want to, make their photos, edit their photos or something like this, I think, interactive tools are definitely, need to get better, and hopefully, Adobe would be on board to make this happen. It's going to be a slow process, presumably, right? But so I think for the foreseeable future, it will be lots of tweaking, but at least we will have artists tweak, not just computer scientists. But in a medium to long term, yeah, I think it will be great to see more user-friendly tools.
Thanks.
Hi, I got a question for Carl about the colorization, the video colorization. According to my understanding, you need a close frame that's colored, a reference. Can you mention an example, a real-life example where this can be applied?
So, sorry, the question is when is it reasonable to copy from a reference frame, or?
Yeah, I mean, I can think of applications where, because according to my understanding, you need to have video that has frames that are colored and some aren't, and you're copying where to color from.
Right. Yeah. So I mean, we're learning to basically point backwards in time to grab a color. There has to be some valid region to point to. If there's not, you probably have to start synthesizing new colors, and maybe a generative model would be pretty good there. And I think everyone's here an expert in that. Yeah. That answer your question?
Yeah, it does. Yeah. Thanks.
Hi, I have a more theoretical question. So from your talks today, what I understood is that the reason why maximum likelihood and L2 loss produce blurry images is kind of well understood, like in the case of variational autoencoders. But how well understood is the mathematical reasons why GANs produce sharper looking images? Is it well understood, or does it require new mathematics to explain it? I mean, why does adversarial learning work so well? I mean, we know empirically that it does, but is there a theoretical underpinning to that?
I guess the answer is the real image looks very sharp, so I mean that's the goal. Yeah.
I presume that variational autoencoders are also trained with real images.
I guess maybe some of this would be hard to formalize, but if you wanted to formalize it, you might think about modeling human perception of image quality in terms of the human being a second discriminator. And you could study how likely two discriminators are to agree on whether an image is high quality. And my guess is that you would find if you've got two neural nets of different architectures, they're more likely to agree than if you have like a neural net and an L2 loss. And to some extent, we might like the output of GANs because the people working on ConvNets have done a decent job of reverse engineering our perceptual system. If we met aliens from Alpha Centauri, they might say, all your GAN images are terrible, what are you talking about? I don't actually know. Maybe there'd be convergent evolution and people from Alpha Centauri would agree. But I do suspect at least part of what's going on is that we have like adversarial examples that do black box transfer from GAN discriminators to the human visual system.
Maybe. Yeah. Thank you. Hi, in fact, I have two questions. The first question is kind of related to the last question about the GAN's performance on images and on natural languages. In fact, in NLP community, people are also trying to use GANs to train models to generate natural languages, but it is less successful than what we get in natural images. So do we have some kind of intuition why this is in fact, the success in NLP is not as good as what we get in natural languages, natural images?
People who work on computer vision are smarter and better looking. It's because for the GAN training algorithm to work well, you want the output of the generator to be differentiable with respect to the parameters. And for NLP, the output of the generator is discrete, so it doesn't have any useful derivatives. Basically, discrete optimization is harder than continuous optimization. I think that's the main factor, making NLP with GANs harder than vision with GANs.
But people also use reinforcement learning to deal with that kind of discrete optimization, but you think that maybe RL is not as good as SGD, so it performs less that good?
Yeah, so partly RL is not as good as SGD, and also partly the places where RL has been really successful, you have a relatively small action space. Like the number of keys on the keyboard is pretty small compared to the number of words in the language that you want to model. And so if you look at some of the things that have worked really well on Atari games or Go, the number of choices you make at each step is smaller than when you're picking words to fill in a sentence. I don't work on NLP, so I might be guessing wrong about what the bottlenecks are, but that's my impression looking at a bird's eye view of both RL and NLP from a distance.
My thinking is that it's just an easier problem, just one-dimensional problems, language, music. We can just get enough data to do okay without GANs, right? So like WaveNet, for example, right? They don't need a GAN because they have gazillions of music samples or text samples, and it might just be that it's just not needed because the dumb data-driven thing just works.
I think another impression I have is, I dabble in NLP myself, that in general, deep learning hasn't been quite successful to the same extent in NLP. Like, simple models based on bag of n-grams already do pretty well, and deep learning helps, but not to the same vast extent as in vision. So even deep learning, I think, has not been quite as successful for NLP.
Okay, so my second question is also related to this. So in GANs, we formulate the problem as a min-max problem. And I want to know, right now we have many problems in GANs, like the training instability, mode collapse, this kind of thing. I want to know whether the problems lies in the problem formulation itself, the min-max problem, or in fact it's lies in the optimization algorithms. We did not solve the mathematical problem that well. In fact, take an example. For example, in NLP we have two kinds of objective functions. One is the maximum likelihood object function, so we can just minimize the cost entropy, this kind of thing. The second one is that we can minimize the GAN loss, which is defined by a min-max problem. So we kind of can see the performance difference kind of from these two mathematical formulations. Another kind of maybe another difference is from the optimization algorithm, because the min-max problem, both the max or the min, in fact, is non-convex, non-concave. So we are not guaranteed to solve both. We are not guaranteed to solve them well. So maybe the bad performance also from the optimization algorithm. So I want to know your opinion. What's the problem really nice and nice on?
I'm not sure. Was your question only about NLP or?
No, I want to know whether the kind of the problems right now in GANs, like the instability, this kind of thing, lies in the mathematical formulation or in fact the optimization algorithms. Because the optimization is also very difficult. It's non-concave, non-convex.
I mean, it seems sort of hard to know until you do something better, right? Take, for example, deep neural nets. People worked on both optimization algorithms and changes to the model family for a long time. And I would say changes to the model family, like moving from sigmoids to ReLUs, adding batch norm, replacing batch norm with group norm, moving from matmul ReLU architectures to ResNet architectures. those all improve the optimization a lot more than big changes to the optimization algorithm did. For GANs, there's a lot of different things involved. There's how do we specify the overall game, how do we specify the models that participate in the game, and how do we actually optimize the game. And there's reasons to think that there are big things to improve in all three of those. So I don't find any way to tell a priori which one is going to give the most improvement.
Okay, thanks.
That's the one last question.
Hi, thanks for the interesting day. Especially on all these artistic and super creative uses of the generator are pretty compelling, but I feel like the discriminator is getting left aside then at the end, and I'm wondering like what kind of creative uses or opportunities are that for this discriminator that birthed itself in this process.
I mean, in the end, discriminator is supposed to just fail, right? In the end, so it's like it's not supposed to be useful, but on the other hand, it kind of is, right? So
yeah. Also, I feel like you can reconstruct the discriminator from the generator. I mean, you can keep the generator and train the discriminator again, so they are kind of redundant. But people have using discriminator for feature learning, but it's worse than an encoder because you can also reconstruct the encoder from the generator. So I feel like you can probably invert each other somehow. Yeah.
There are some people who use discriminators to evaluate the quality of text in NLP. I think the people who did the smart reply feature for Gmail used that in one of their published papers. Another thing is you can do semi-supervised learning. You can train the discriminator to say which of the real categories the input is in, as well as whether it's real or fake. And that approach tends to work better if you have only a small amount of labeled data to learn from and a lot of unlabeled data in addition to that. So those are some ways you can use the discriminator. I know they're not artistic, so it doesn't fully answer your question.
Right. I mean, even if the discriminator is more useful than general L2 for some problems, I was thinking that might be a nice use. I don't know if that's been seen a lot.
A couple other things I could think of. So in the theory I presented, the support size of the learned distribution, the generated distribution, grows with the discriminator size or discriminator capacity, so that's one way. And then also I think in the domain adaptation work, I think implicitly you're working against a class of discriminators. I think it was Jody, yeah. So the discriminator does seem to be useful.
Okay, thanks.
all right, well, let's thank the organizers and all of the speakers for a wonderful day.
Yeah, so all the slides will be online, and we are looking at the future version of this event, either a tutorial, workshop, course, probably not a conference, but and so any constructive comments and feedback will be largely appreciated. Thanks again for attending the tutorial.